Hi everyone and welcome to this new video. In this video I finished the Enigma project. So this project was started some months ago and I showed how to implement the Enigma machine in C using a header-only library approach. So basically this is our library, and here are some links to test out the encryption. And so here we have implemented our Enigma machine with our rotor, the blackboard, the reflector, and finally the Enigma itself. Of course, there were some things here that could be improved, but this is like a general first implementation which aim to showcase the main encryption logic of Enigma. Here in this function, apply Enigma, which basically encodes the core logic of the machine. Now, in this video instead, what I want to showcase is how we can implement a command line interface to use our machine. And here I've already the code. If I do make on this project, and then do example CLI, as you can see here, we open up this Enigma CLI. And here we have a bunch of different commands like quit, help, info, set, encrypt, decrypt. Like for example, encrypt hello, and it's going to give me the encryption of hello. And then if I do info again, notice how before and after the encryption, the rotors have changed position. Because here the position of the rightmost rotor before was 0, now it is 5, because it has encrypted 5 different letters. And so in this video, I want to showcase exactly how we can implement such interface. So basically, I want to showcase how to implement a command line interface using the C programming language. I hope it is useful. I hope you get something out of it. If you have some feedback, criticism, and things of the sort, feel free to share in the comments. And if you want to support my project, there is a Patreon in which you can use to support my activity. Thank you very much and enjoy the video. Okay, so having said that, let's get with the implementation. So here is a simple clip for showcasing the Enigma library. I've included libraries from the standard libc and from the readline library. Now here we have to include the Enigma library, right? And Enigma sits in the previous directory, so here we have to do this. However, remember that Enigma is a header-only library, which means that this header contains both the declaration of the functions and of the data structures, and also the implementation of such things. Here, if you go down, we find this Enigma implementation, and so we need to include the Enigma implementation. So we need to define the Enigma implementation directive, so that when we include the enigma.h, it's actually going to include the code. Okay. And then here I'm defining a max number of arguments, which is going to be 129. And so this is good for now because it's fine. We're going to fix how many arguments we can take. So in this first portion, we're going to define some data structures and some headers and some functions which are useful to us. So in terms of function, basically, what do we have? Well, we have a function which is going to parse the arguments taken from a buffer, taken from a string, and it's going to return us a command. And what is a command? Well, a command is a simple struct which has a command type, so we have a type of the command, we have the arguments that we parse to obtain that command, and then we have the number of arguments. So, and this is why we are hard coding the length of the arguments to 128, so that you can have fixed buffers of car pointers. So this is basically a command. We're going to have a type, the argument of this command, and then the number of the arguments. So that's the first thing that we will do. Now we have a utility which return a command type. It's going to be called string to command type. So here we pass a string into the input, and it's going to convert it into one of these command type. Now, what are these command type? Well, this command type is an enum, so command type is an enum, and here we have the different commands that we will implement. Now, for example, cquit, chelp, cinfo, cset, cencrypt, cdecrypt, decrypt, and cunknown. So these are going to be the different commands that we will implement. Of course, in the future, you can choose to extend this to have more commands, to use the machine in different ways. but this is like a pretty basic usage of the Enigma machine. Okay, so we have these two functions initialists that are used to create the command, and then we have the functions that actually implement the various command. Now, these functions are going to have the same signature. So they're going to return a void, they're going to have a pointer of arguments, and they're going to have the number of arguments and args. And notice this is actually a double pointer to the arguments. So we're gonna have execute quit, we're gonna have execute help, we're gonna have execute info, set, encrypt, and decrypt. So info, set, encrypt, and decrypt. So one for the command right in here. Here we have 6 commands, and here we have 6 different functions. Now, at this point, we can instantiate a global object, a global pointer to an Enigma machine. So this is a pointer. And here we have a table. So here we're going to have something that is, I would say we have to be careful with this thing. Because this is going to be an array. It's going to be an array of function pointers. So an array of function pointers. Now these functions are going to have this signature, so return type void and these arguments. So how do we do that? Well, the array is going to be called a CLI action table, and it's going to be an array, so we have to do this. However, it's going to be an array of function pointers. Now to define an array of function pointers, what you do is you put a star in this name, you put parentheses here, and then you put the return type of the function on the left and the arguments of the function on the right. This is a little bit of funny syntax, but it works, and we can just declare and define it in the same position in the code. Here we're going to have cquit equal execute quit. We're going to have chelp equal execute help. Then we're going to have all the other stuff like info, like set, encrypt, and decrypt. And of course, here we have to have decrypt, encrypt, set, and info. So this is gonna be our approach to basically have this sort of like dispatch table, right? This is a dispatch table because when we're gonna use it, we're gonna give to this table one of these enums, which is just an index in the array. Actually, here I have to say encrypt in capital letters and decrypt as well in capital letters. So I'm gonna use the enum type as a dispatch. It's gonna give me the function pointer, and then I'm gonna use the function pointer to actually call the function. So that's the idea. Basically, that is the whole idea. So this is a first thing, like these are two things that we will use. Now, when it comes to at this point, we can actually go and define the entry point of this code so that you can test it out to see if we've made any mistake. So it's not going to take any arguments, this CLI, it's just going to be a simple CLI, like no arguments. Now here, I'm going to define a simple default Enigma. So I'm going to do Enigma equal init Enigma. I'm going to initialize it with what? Well, here to initialize it, of course, I need to put various elements in the initialization. Here I need to put, actually, let's see in the source code. Init Enigma, here I have the rotor names, the rotor positions, the ring settings, the reflector name, the blackboard, and the blackboard size. So it is a little bit messy to define, but we will get through it. So we have the first one is going to be rotor names. So M3, Choo-choo is the first rotor, M3-1 is the second, and M3, III is the third. So this is going to be the rotor, and I'm going to cast it to a const char like this. So this is rotors. Then I'm going to have the rotor position. So this is going to be a const uint t, and here is going to be rotors number. Now this rotor numbers is defined in here, rotors n, it's the number of rotors. So this time what do we have here? We have the positions, we're gonna be 0, 0, 0, 0, 0, 0, rotor positions. mean, to be honest, I think I can improve the library by just having a default initialization because it's kind of a mess, but it's fine for now. Then I have the rotor ring settings. Rotor ring settings is the same thing, 000. Then I have the reflector name, and by the way, here I have to put a comma because they are arguments in the function. Then here I'm going to put M3B, which is going to be the reflector name, and here I put a comma. Now here I have the plugboard switches. So the plugboard switches is going to be a matrix where we're going to have two elements for each, two columns for each row, basically. So here we have that A goes to M. We're going to have that F goes to I. We're going to have that N goes to V, that P goes to S. We're going to have that T goes to U, and that W goes to Z. Here, W goes to Z. So this is a way to define the mappings on the plugboard. And finally, the plugboard size, which is 6. So this interface is not that amazing. I know I'm gonna have to improve it in the future, probably. But yeah, for now, we are good. And with this, we have created, we initialize the Enigma machine. At the end, we're just gonna do destroy Enigma with Enigma. So this is it for now. And let's actually see if it compiles. Let's do make. So of course, here I have undefined references. I cannot use them. Makes sense, because I need to define them. So let's define them with stubs. So let's just copy this. Let's just paste it here. And let's just, let's do a query replace with this. I'm gonna do this, this, this. And then here actually like this. And I'm not gonna use anything with them. Okay, now I do make, and now it does work. So we have all the stubs that we still need to implement, of course, but now the code compiles. Of course, it does nothing because we just initialize Enigma and we destroy it. However, it is exactly here where we will put our REPL, our read eval loop. So here we put the REPL, and how is this thing gonna work? Well, we do done. We have a simple variable done. While we're not done, we're gonna keep looping, and we're gonna say, we're gonna read the line from the prompt. So this is the user input, basically. Then, if the buffer is equal to null, we're gonna just say terminating process. So there was some error in reading, and we're gonna exit. And technically, we need to destroy Enigma, but you know, like in this case, the operating system will take care of it. Okay, but I guess let's just make it a destroy Enigma here, or let's just do something. Go to close, and then here we put a close label. A close label, but of course in this case I would lose it. So let's just say exit 0. So let's just say exit 0, and we put a destroy here. We put destroy there, so that's fine. Now, the next thing we need to do is we need to parse a command. So we do command cmd parse args of buff. So we're gonna take the line that we read from the user and we're gonna parse it into a command structure, right? Now, if the command structure is equal to unknown, if the command was not recognized, then we're gonna print. Actually, here I guess we can say not really Enigma like this, we can say info terminating process. Actually, we can say error reading line terminating process, because technically that is an error situation. And here we can say error, we can say unknown argument, unknown command. But this time it's not an error. I mean, we can handle this. We can say Enigma unknown command type help for documentation. And then we put a dot. So we do this, and we don't really destroy nor exit. We just do this and that's it. Otherwise, if the command is known, we execute it. We execute it with the function execute cmd. At the end of the day, we're gonna free the buffer because read line allocated memory, now we need to free it. So that's the idea. So this is a very simple REPL that we can implement. Now let's check it. Let's check if everything works fine. Let's just make it. Okay, of course, here it says, look, C unknown is undeclared. I've written it wrong. It should be like this, to be honest. So that's the first error. Here it should be like this, and here it should be like this. Okay, here it's fine that I don't have that. Okay, so that one is good. And the other error is that, of course, the execute CMD is not defined. Because the execute CMD, I did not define the function execute CMD, which is totally fine. But basically, this function is going to be like this. It's going to take a command and it's going to execute it. And it's going to be the top of all the different types of execution. Okay, so at this point, if I try to compile again, let's to make, it says, okay, execute CMD, you need to implement it, of course. So let's just put it here as we did previously with a stub, basically, that does nothing. And then we have undefined reference to parse args. Of course, another function here is parse args. We also need to define this. So let's put it here. And we also need to put, to be honest, a string to command type. String to command type. Okay. Okay, perfect. Now we have some warnings, but that's fine. Now we can go example clear. It's gonna start this, but it's not gonna print anything. Why is it not gonna print anything? That's interesting. So, because parse args does nothing. So actually this thing is really not defined because here we are returning nothing. Okay, so that's not good, so to speak. Okay, so let's actually implement this parse args to parse those well-damned arguments. Okay, so parse args, how are we gonna handle that? So here we're gonna create a command, so let's just create it here, of course. Now, what we're gonna do here? Well, here we're gonna use the standard C library strtoc, which is used to tokenize a string. And we can check it with main strtoc. So basically, it's gonna be extract tokens from string. So the strtoc function breaks a string into a sequence of 0 or more non-empty tokens. On the first call to strtoc, the string to be parsed should be specified in str. In each subsequent call, should parse the same string, str must be null. So the first call, we're gonna have this. We're gonna have cmd str, we're gonna have strtoc, buff, and here we want to split for the white space. Then the type of the command we're going to initialize with the string to command cmd string to command type, sorry, so this function, basically, this function. That's how we get the type. And then here we just count the arguments. So we do a while. And what is the condition for the while? Well, in this case, the condition for the while is while I is less than max args. So that's one of the condition. And we have C-args of I minus 1 is different than null. That is, we still have to obtain something, we still have to parse something. After the loop is done, here we do C and args equal I minus 1, and then we return C, because the last arguments was actually null, so it was equal to null, and so we don't need to care about it. Now, what do we do to parse it? Well, we just do cargs I++, and then we do equal strtoc null, and then the white space once again. So here parse the arguments to the command, here extract the command. Now, how do we implement this string to command type? Well, this is a very simple switch, pretty much, but in this case, we're gonna call a bunch of str compare, because we are going to compare the CMD with help for. So basically we have this thing, then we have all the different commands, all the different manifestation of the commands, like quit info, set, encrypt, and decrypt. So of course, help, all they have the same length. Here they have 3, and here they have 7. 7 and 7. And we're going to say if this is equal to 0, we do something. Else if this is equal to 0, we do something. Else if this is equal to 0, we do something. and so on and so forth. So it's like a long list of things to do if that is equal to 0. And the first time that we get something equal to 0, we're actually going to parse that. We're actually going to use that. Okay. And of course here, we do return chelp. Return C, you know, all kind of returns. And otherwise, if you do not match anything, you're going to say return C unknown. Here is decrypt, here is encrypt, here is set, info, and quit. So basically something like this. And with this, actually, we are able to, we have this implemented, so let's see if we made a mistake. Okay, seems to work. Now, if I do ask, it's gonna say unknown command. Actually, in this unknown command, let's not put the prompt. Let's just put like all this space, but I want all this space in white spaces. So like pretty much like this. Okay, like this. So that here I do quit, whatever, I do make, then I do example clear, and it says unknown command. Then I do help. It's not gonna do anything help, but at least it recognizes that I've called help and not any other command, so that is a good stuff. So basically, at this point here, we just have to implement the main dispatcher, execute CMD, which we call from the main REPL here, because once we get the arguments, if it is unknown, we're just gonna print it, look, this is unknown, I don't know what to do with it, otherwise we're gonna execute it, right? So this is the main dispatcher. Now, considering how we implemented the table, here we have already a dispatch table ready to be used. So in the CMD command, in the execute CMD, what we have to do is simply use that thing, because now we have a struct command that is ready with the type and the arguments, and therefore we can actually do as follows. Clear action table, here we put CMD type, so we are using the type to understand what is the function pointer to use. At this point, this is a function pointer, we can actually use it with the parentheses with CMD args and CMD and args. So this seems a little bit convoluted, but it's actually pretty simple. Here we are obtaining a function pointer with this table. Because remember, this is a table of function pointers. Once we have the function pointers, we can actually call that function with the arguments and the number of arguments that we obtain, and all this information is stored in the CMD struct, in the command struct. And so with this, now the only thing that we need to do is just implement the different commands, basically. For example, how do we implement quit? Well, here we're gonna say, let's say that here I have this number of spaces, which is useful to just know. And here I'm gonna say execute quit, I'm gonna put those number of spaces, and I'm gonna say about to exit. And then here I'm gonna say exit of 0. Actually, technically speaking, this I can just set I would say what I can do here is to make sure that I still free the memory, I can actually I can put done as a global variable, which is equal to 0 at the beginning. And then I can just, in quit, I can just set done equal to 1. So done equal to 1. So let's see if this works. This could be a better design. So I do make. Of course, here I have to put done in capital. I do make, then do example clear. I do some command, I do quit, about to exit, and then it exits. Now, of course, you will need to test it much more thoroughly than we're doing, but this is just an example. So in this way, here, we have implemented our first command. And the rest is just, implemented a specific logic for these different commands. And you can do it as ever you want, but that's pretty much the skeleton. Now, let's implement the help, the documentation, right? So to do the documentation, we just need to do a bunch of printfs, basically. And here we can say list of commands. And then here we put a little bit of space, and then we're gonna say, for example, quit exit from Enigma. Then we have quit info set quit help info set, and then we have encrypt, and then we have decrypt. So encrypt plain text, decrypt ciphertext, and here I write, I mean, this is pretty obvious, to be honest. I don't think we need to document it further. Okay, then we have set. For example, for set, we can say set rotor or reflector, set reflector or set plugboard. So here we have a bunch of different settings. Then we have the print Enigma, so print Enigma configuration, and then here we have the list available commands. So that is the help menu, and then at the end we have a new line, so just a bunch of printfs. Then we have the info. So this is where we are gonna print out the information, the current configuration. So here we say current configuration. Here we say rotors from left to right. And then here we just printf this kind of things. So we say, we're gonna say rotors from left to right. Let's say percentage %s, percentage %s, percentage %s, new line. And then here we have the Enigma rotors 2.name, 1.name, 0.name. Okay. Then we have the rotors, the position. Rotors, okay, here I guess I'm gonna just say positions from left to right, and here there's gonna be numbers. And here I'm gonna say position, 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 and then I'm gonna say ring settings. Ring, 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 ring. Okay. Then I have the reflector, which is another printf away. Printf, so reflector is gonna be a simple /n like this. Enigma reflector name. Reflector.name like this. Then we have the plugboard. The plugboard, which is, here I have the printf, plugboard, percentage %ld plugs, and then here I say plugboard dot board size, and then finally here I iterate over all the different board size, over all the different elements in the plugboard that have been configured, and then here I print a little bit space to the right. I say %c, then new line, and then here I actually have this. I have Enigma plugboard.board I of 0, and then I of 1, but this thing has to be code to char. Code to char, so here I want to extract the actual character of the English. And then here I actually close the printf. And then here I return. I mean, the return is not even needed. So this was a bit of code, so let's try to compile it. So let's see what's going on here. Okay, here I have a bunch of simple errors, like commas here for the arguments. Okay, then in 120, okay, here, I don't need this last, I don't need this last, and I don't need this last. Okay, now it works. Let's try to do the info. Here I have current configuration. So rotors from left to right, positions, actually let's do like this. Here I have rotors from left to right, and then I want to put a new line, and then maybe I want to put something like this. And I'm gonna say, here I'm gonna say percentage %s, percentage %s, percentage %s, okay, like this. Like, so that I pretty much have like this, basically. positions and ring. So here I have just rings. Okay, let's see now if it's a little bit better. Make. Okay, what's going on here? It's not percentage S, but of course it's D because it's numbers. These are number positions. So I do example clear, I do info, it's rotors from left to right, positions, okay. Maybe a little bit of space just so that it is a bit more clear, like this amount of space. Example clear, then I do info. What's going on here? Oh, too much percentages, suppose. Okay. Info, okay, so we have rotors, positions, rings, we have the reflector, and we have the plugboard, and of course in the plugboard we need to end it with the other letter. Okay, so now it actually looks fine, at least to me. Now, let's implement the execute, encrypt, and decrypt, because the set is going to be the most annoying one, the most complex one of the bunch. So how do we encrypt stuff? Well, here we have to have at least like more than one argument, because otherwise I'm gonna say encrypt requires only one arg, the plain text to encrypt. Actually, yeah, here we only need one argument. So if it's different than one, we have a problem and we cannot use it. Right, and here, by the way, we can put this kind of padding into the message so that it's equally spaced out. Perfect. At this point, we can extract the arguments from the double pointer here. We can extract the various arguments. So here we're gonna do this. Then we're gonna say plain text length is gonna be str length of plain text. This assumes that plain text is null terminated, but it is because we obtain it from the strtalk function. Here we defined a ciphertext, and here we copy the plain text into the ciphertext. We also copy the null byte. And then we perform the Enigma operation. Enigma encrypt. We say Enigma plain text length ciphertext. And then we printf the ciphertext, basically. And so here we have our execution. We are extracting the arguments. So basically it's like this. We are extracting the arguments here. We are creating the ciphertext. We are initializing the memory of the ciphertext. And then we are performing the encrypt operation from plaintext to ciphertext. And then we are printing the ciphertext. Notice that here we are not really allocating dynamic memory because this lives on the stack frame of the local function. Therefore, we do not need to deallocate it once we are done. And the decrypt is going to be pretty much similar. It's just that now we're going to have not the plain text, but the ciphertext. And so plain text here can be replaced by ciphertext, and ciphertext is going to be replaced by plain text. So plain text, and here we have plain text, and here we have plain text at the end. And here we have plain text. So it is pretty much the same, it's just that like from here to these two functions only differ because here, for example, we find a plain text and here we find a ciphertext. So we just swap around plain text with ciphertext. And we have our execution. Enigma encrypt, and notice that, okay, here we actually have to do Enigma decrypt, sorry. We have to do Enigma decrypt. And basically that is the idea. So we do that. And in terms of encryption and decryption, we are pretty much good. I mean, internally, Enigma is a symmetric cipher, actually. So it performs the same operation, because if you look at the implementation, both Enigma encrypt and decrypt, they actually called apply Enigma. So it's literally the same call. It's literally the same call. It's just that it differs what is the input and what is the output, but pretty much it is the same call. And so here we have these two things. Let's try the encryption and decryption procedure. So let's try to do this. I'm gonna say encrypt hello, like this. And then we're gonna quit. We're gonna say decrypt this thing, and we're gonna say hello. Notice that we have to quit because let's say that we encrypt hello. And then we want to decrypt this thing. It's actually not gonna give us back hello. Why? Because after encrypting, the internal state of the machine has been changed. Therefore, decryption does not work. To decrypt a string, you need to bring the machine back to the original state that it was used to encrypt the string. So be careful with that, otherwise it can get confusing. So the last thing, and then we're done, is, okay, let's actually do the set. Let's actually do the set Enigma, which is the execution set function, which is one of the most annoying functions to implement. Okay, so let's implement execute set. Now, once again, here we have a bunch of conditions. We say if this is less than 1, it's not good. So set requires at least 1 arg. So basically, we cannot get away with just 1 arg. Then we have the set type. So we're going to extract from the arguments the set type. And then here we're going to do a bunch of str compare set type rotor 5 else if, and then here we're going to just iterate over this structure basically. So we're going to iterate over this thing. And we're going to say rotor is one thing, reflector is another thing, and plugboard is another thing. Else, and then we say, we just printf and we return. Here we say, for example, set accepts only the following args: rotor, reflector, plugboard, because this is going to be used to, change our machine basically. So in this case, we're going to call an internal function set rotor, sort of like we have another dispatching mechanism. Here it's going to be called set reflector, and here it's going to be called set plugboard. And of course, here the length has to change because plugboard is 9 and reflector is also 9, while rotor is 5. So rotor is correct. So at this point here, okay, we need these 3 different functions. We need the set plugboard, set reflector, and set rotor. So we say set rotor, char args, size t, and args. So this is one. Then we have set reflector, and we have set plugboard. Now, let's go for the simplest one, set reflector. So the set reflector is going to be like this. We are gonna check if we have set requires at least 1 arg, set reflector, reflector name. So basically like this. And then here we say reflector name equal args plus plus. We're gonna decrement the number of arguments. We're gonna say init reflector Enigma reflector name. So here we're just calling Enigma functions that initialize the various elements because this is just an interface. So that's the idea. Now for the set plugboard, we have set plugboard. The syntax is going to be like K1 V1. Then we have K2 V2. Then we have K3 V3. So we have key values pair. So we're going to say, I'm going to say size t board size and args. We're gonna do uint8 board size of 2. So this is a new board. And then here, we're gonna iterate over the board. I++. Actually, here is, board size. And then here we extract the first element of the board by saying, here we are doing like this, minus. Then we're doing the second based on the first string. So which means that here we can just put null. It's going to be the same. And then we initialize the board. I of 0 is going to be L1 of 0. I of 1 is going to be L2 of 0, I mean, these are just one element, one characters. So that's the idea. And then we say init blackboard enigma board size. And then here we just check if nargs is less than 0 or nargs is greater than 11, we have a problem. So basically, in this case, we have a problem and we just print a kind of error message like a guard. And in this case, we say set reflector requires at least 1 args and no more than 10 args. Basically, because we have I guess a limit for the blackboard size. And so here we have set reflector, set blackboard. Let's see if we make any mistake, by the way. Okay, seems good. And finally, we have set rotor. So set rotor, it is the latest one of the bunch. So what do we have here? Well, the syntax is going to be set rotor is going to be rotor name, position, and ring. So actually, and here we have index to swap, because we have 3 rotors, so we have to tell which rotor to change. So we have rotor name to swap, args plus plus, and then I do minus args like this. Then I have rotor name, position, and ring. Rotor name, position, and ring. So here I'm popping elements from the args buffer. Then here I'm going to define this rotor index, rotor position, and rotor ring. And here basically what I say is if here I have a bunch of str compare. So let's see if we can just take this code in here. It's going to be similar. It's just that instead of set type, here I have rotor index to swap. Not here, but wait. Instead of set type, I have rotor instead of setup like this. I have rotor index to swap. So here, here, and there. Here I have left, middle, right. So it's 5, 6, and then 4. And here I say rotor index equal to rotor index equal 1, rotor index equal 0. Like this. Else, here I say rotor index must be either left, middle, right. Okay. Okay, so that's the idea. Then here I do rotor position atoi pos, so I convert this, and here I'm gonna add a to do. Add more checks in case of failure. So atoi simply converts the value into an integer, and same thing for rotor ring, atoi ring. And then here I am pretty much almost done, because here I'm gonna check some like error conditions. Rotor position is less than 0 or rotor position is greater than 25, then we have a problem. And rotor ring is less than 0 or rotor ring is greater than 25, here I have a bunch of problems. And here basically I'm gonna do similar to this. I'm gonna say rotor position and ring settings must be positive integers between 0 and 250 and 25. Between 0 and 25, and here I return. And here finally I'm gonna do a rotor init. Here I'm gonna put the rotor index to swap, rotor name, rotor position, and rotor ring. And so with this, I have almost done, because here I need to put, I think here I'm gonna say, wait, this is execute set. Execute set, execute encrypt, wait a second, I should have put it set rotor actually. So here I confuse myself, perfect. So here, set rotor, okay, here I have pretty much this thing is actually supposed to be here. Set rotor. Yeah. So for some reason, rotor index, okay. While this thing instead is supposed to go down. So I don't know why that thing happened. To be honest, maybe I was rushing too much. But yeah, so like basically in execute set, we have, and here is rotor, reflector, or plugboard. Okay, so here we have this thing. Then we have set type, and then here we dispatch based on the set type. Perfect. And then we do set rotor, set reflector, set plugboard. Now, set plugboard, okay. Set reflector, okay. And set rotor, here we are extracting the arguments. We are using them, we are initializing the rotor index, the rotor position, and the rotor ring. And then here we are putting some checks here. And then finally we are initializing the rotor. Now the only thing we need is if here the arguments is less than 4, we're gonna return. We're gonna return and we're gonna print something like the following. We're gonna print like set rotor requires at least 4 args. Set rotor, rotor index, rotor name, position, and ring. Index, position, okay, index, name, position, and ring. So, this is it. Let's quit. Let's compile. Okay, here we have some problem. Rondor index to swamp, CLI 168. So 168, rotor index to swap, not name, but index to swap. Okay. Then we have atoi ring, atoi pos, position and pos and ring. Okay. Okay. Now let's do info. So let's do set set rotor. I'm gonna say 0. So the one on the right, I believe. M3 1 0 0. Okay, no, set rotor left M3I 0 0. Unsupported rotor. Okay, yes, because I've written it wrong. So I have to say set rotor, but here I have to say M3. I like this. Okay, okay. If I change, for example, I do set rotor left with a ring position of 1. Okay, here is actually changing the configuration. So it seems to be working. Then here I can encrypt stuff. Hello, we have the encryption and I can decrypt that. And that's a first approach. Now this code is not the best code, of course, you can improve it if you want, but this is like a simple implementation of a simple command line interface in C using this dispatch method based on arguments. So this is the code that we use to dispatch. And then we have for every function the different implementation for that functionality. So I hope it was fun. I hope you learned something about it. If you want to support my work here, you can subscribe on Patreon. And I also have courses where I teach about security. So web security and also Linux security. And in the future, of course, I'm gonna make more. Thank you for watching and to the next video.